So let's continue. So we have seen one major source of foreground. Usually one has a problem with background, but we want now the background. So we want this noise. And the major source of foreground, of course, if you want to measure such fine stuff, is our sun. So that's like why we go to the Lagrange point. And then we have another problem. We observe now, and then we want to look back through time to this 400,000 years after the Big Bang. The problem is that in between there are plenty of light sources which very likely often still have a sufficient of radiation in the microwave. Microwave, radio wave. Remember, these were these big telescopes that are somewhere like this James Bond film when they have this final fight, I think it's called, in golden eyes at the end in this telescope, in this massive concrete bowl in Puerto Rico. This is a radio telescope. So we have these sources that are before us. And so how now to distinguish? We have no problem. Life is not easy. With Kobe, well, one used basically what was known before and tried to subtract it. With WMAP, one just looked into 5 other parts of the electromagnetic spectrum, so other frequencies, and hoped that the other sources, the foreground, would be there more intense, and then one subtracted and ended up with this picture by WMAP. So one way, of course, all people thought it works. So for the Planck satellite, one simply makes it better by having more frequency regions. And then you see the different radiation of the Milky Way, and it's of course, Milky Way is not just flat, it's extended. Therefore, we see it a bit above and below the equator of this or the plane. And then we see here that some of these objects are more or less intense in different frequency ranges. And now we can basically peel the foreground away and end up with this stuff here, the baby photograph of our universe. And then we look at this temperature variation at the millions of a degree scale. So microkelvin, millions of a degree, plus or minus, towards this uniform background distribution by Penzias and Wilsons. And what we get is these freckles. And somehow the spot size seems also to matter. But what is happening here? Well, beforehand in the light-dominated universe, basically every time the cluster of matter would have formed, light would have come and dispersed it. Light has a small pressure, but because there's so much light, this is like a dictatorship where people assemble and immediately a policeman comes along and disperses basically the people. So you're not allowed to form a crowd, and the policemen are the photons and the people are the nuclei or the matter. So this can only happen that you form now clusters of matter where the visible matter is a bit more attracted and forms a surplus of matter, what means there is a bit less radiation. It appears to be a bit less intense, a bit colder. Only if there is matter that interacts with the other matter via gravity, but not, it's itself is not interacting with radiation, with electromagnetic radiation. That's what we call dark matter. So these spots shouldn't be there if there would be no dark matter. And because they are there, we say it must be dark matter. So, well, interestingly, we knew already about dark matter beforehand. That there is dark matter. We don't know what dark matter is, but we know it's there. And where? This was done by Fritz Zwicky and Berta Rubia. We will come back to this plot. What you see here is the velocity profile. So with which velocity the particles in a galaxy rotate around the center of a galaxy as function of the distance. So inside, where we have basically parts of the stuff that is in us, this is basically pulling inside, and the other stuff that is outside pulls outside. We would expect, so the net that is really pulling is the stuff inside, and we have usually a 1 over r squared behavior. But now we would approximate this mass inside with density multiplied with a volume. Density is mass per volume. So we multiply now the volume over. A volume of a sphere is r to the power of 3, and we divide by r squared. So we end up with r, we get this linear increase. And for distance further away, we would expect there is a 1 over r squared. So stuff that is outside of the galaxy, we would expect a 1 over r squared. So this hyperbola. And in between a bend over region. Now, if we take the starlight and use basically the Doppler shift, that here the stuff, if it's rotating this way around, it's moving away from us, so it should be redshifted. Here it's coming towards us, should be blue shifted. This here is 90 degrees, should be no shift. So we can get here a radial dependent velocity profile. And that's what we expect from the visible matter. What we have is all these stars are much too fast, or are too fast. Even the inner ones, but in particular the outer ones. If you look here, this is far too fast. And then there is gas around. You have everywhere gas, even in the intergalactic space. There you have usually one atom or molecule, mostly atoms then, per cubic meter. So in 1 meter, you find one particle. That's a vacuum we dream of on Earth, but it's not a complete vacuum. There's still something there. And if you think about the gigantic dimension of intergalactic space, there's still some matter there. But of course, you find the nearby galaxies also. There's mostly hydrogen. And hydrogen has one particular line, which we will later come back, this 21 centimeter line, which is in the radio waves. And from the Doppler shift there, we can again calculate back on the velocity profile. And this is certainly not fulfilling this stuff. From this observation by Fritz Zwicky and later Berta Rubia, we could already infer that there must be about 5 to 6 times more dark matter than visible matter. Visible matter is then the stuff that we know: electron, proton, neutron. Neutron, you could now say it's electrically neutral, doesn't interact with light. That's not exactly true because it's magnetic charge. And we talk about electromagnetic wave, which interacts a bit stronger with protons, but and less with how to say, well, a bit less strong, or stronger with protons than with neutrons, but it still interacts with neutrons. it doesn't interact with these neutrinos. If you remember back cosmology, at the end I show you this elementary particles, 6 quarks, 6 leptons, electron, muon, tauron, and 3 neutrinos. They were a good candidate for dark matter, but it turns out their mass is not enough. We know there is 5 to 6 times more mass. Well, we also know this from gravitational lensing. If you remember, if you have mass, it deforms space, the light is bent. And if there's an object behind another object with a strong mass, like a galaxy, and behind there is another galaxy, we get these Einstein rings in the best case, otherwise we just see a distortion of the object behind. And from this distortion, that's usually much too much for the matter that we see. So this, we know that it's about 6 times more. Okay, there is then this dark matter, which obviously made these clumps that we now see here as darker, as bluer spots in the cosmic microwave background. And this is no perfect. This is basically the starting condition, how the matter distribution as we observe it nowadays, which would be in here, this is just clusters and super clusters and super clusters of super clusters, and these voids, and then suddenly this emptiness. So you have this gigantic accumulation of matter, and then suddenly nothing. Then you have these connecting strings, but this here is now the perfect basically start condition in order to check for any simulation that deals with the dynamics of the universe to reproduce this. And what do you have? Basically at some point the gravity, as used Newton basically, or if you want to use Einstein, deformation of space, it's a bit more complicated but still works. And this is done, for example, in the Boy-Scholl simulation. Boy-Scholl, what would you think now? What is Boy-Scholl? So basically, this is shown down here. So we have this very dense, small universe. Then it expands, and we get this structure of the matter distribution. There's matter accumulations and rather empty parts of the space. And what you see at the bottom, this is parts of the Boy-Scholl simulation. Boy-Scholl, I would associate this very famous ballet and theater in Moscow. Now I'm married to a Russian. My wife is, not to a Russian, my wife is Russian. So occasionally I got to listen to words like Popa Bolshoi or Popa Bochin Bolshoi, and this time, of course, you check up. Popa is a part of the body, which you usually should not name somebody. Bochin means very, and Bolshoi means big. But this is when she's just mildly upset. When she's really upset, she calls me Sarasa, which means pest. So back from this degrees of intermarriage, verbal interaction to the simulation. And this Boy-Scholl theater, Boy-Scholl simulation, what means the big simulation of everything, is very successful, even down to the formation of galaxies and the structure of galaxies. Unless you consider the position of globular clusters. There it has problems. But for the big scales, Bolshoi, it's obviously not too bad. So this serves us as a very good starting point, and since it works out, we can say, okay, there must be something true to it. But it's getting even more mysterious. We have seen this inflation suddenly of this re-accelerated inflation of the universe, which can be taken into account with Einstein's cosmological constant, this just-in-case constant, the biggest blunder of his life. And here it comes into game that we need this freckle size. What we have here is basically the inside, if we sit in the center of a sphere around us, the night sky. The equator here is the plane of our galaxy. And now this freckle size, so that we have these bigger structures and the smaller structures. So now what we can do, we can use the mathematical functions of single harmonics or spherical harmonics. You have the phi angle, which is basically around the equator, and this theta angle, that is north-south pole, and then the angle between the direction we are looking at and the north pole, the connection to the north pole. And what we have here is this cosine or phase factor in the equator plane, and this PLM, these are the so-called the Legendre polynomials. For the physicists in future, if you hear spherical harmonics, open your ears, it's something very important. And now they are basically characterized by this L and M. For us, this L is important. If we look in L, this is the so-called multipole order. L equals 0, no pole. It means just a charge, for example, in electrodynamics. Or something that is homogeneously distributed. L equals 1. This is then always 2 to the power of L, gives us the number of poles. So L equals 1, 2 to the power of 1 is 2 poles, dipole. Hot, cold. And then this M gives us basically some orientation. So here would be also M equal, there also the negative M's are possible. M ranges always from minus L to plus L in integer steps, but this is then later on. So what is here, the essential thing is, you see now, this is just the orientation that happens, or which really makes or somehow the orientation. But what stays relatively constant is the size of these reddish areas and bluish areas, more or less. So, and this obviously dipole plus minus, plus minus minus, plus minus plus minus, plus minus plus minus, plus or minus and bottom plus, so 4 poles, the quadrupole, the L equals 3, the octupole, 4 times hot, 4 times cold. But what we see is that the size of this hot blue is now strongly L dependent. That means if I want to have finer details like L equal 10, obviously the freckle size is smaller. So if I want to go to very high of these L's, these multipoles, then I need to have a very good angular resolution and do it nicely for the spot size. So the bigger the spot size, the lower the L, the higher the L, the smaller the spot size. Okay, that's motivation obviously for Planck compared to WMAP, because there we have now much finer freckle size. And the next is we plot basically how much of these freckles with a given size do we have. And here a big one, like this bigger scale stuff, still contains freckles of smaller size. So it can be also built up of smaller sized freckles. So how many of them do we have relative to the others? These numbers we plot now to the top over this L, over the freckle size. So the number over the size. This is basically done here. And see the big resolution, the dipole, L equal 1. Hot cold. Remember this millikelvin scale. Okay, and then we increase the L, what means we shrink the freckle size. This gives us such a curve, a power curve. And here is basically the anisotropy power, what means how many of these freckles of a given size. What we get is an experimental value. And then we can take our model about the inflation of the universe and feed in things like matter, that acts via gravity, but has this electromagnetic interaction, then dark matter, and maybe put in some stuff that says that reaccelerates again, that works basically against gravity, and call it dark energy. We can put in how much light, or the total energy density that would work gravity-wise, which includes even the massless photons, what I don't understand, but there are smarter guys that certainly understand this. And we get a model description, which we call the lambda, because it contains now this cosmological constant via this dark energy that seems to work against gravity and therefore accelerates the expansion again. Cold dark matter model. So somehow the standard model of cosmology, why cold dark matter? These dark matter particles need to have a certain size compared to the other, relative to the other visible matter. If they are too small, you give them a small ping and they are immediately very fast. And now when you have two very fast runners passing each other, do they interact? Do they cluster together? Not much to do for the police. But if you have two relatively low ones that see themselves relatively long, they might start talking to each other and start to build a cluster, and then comes a third one along and joins in the conversation and so on, and to build up. So you need something that is low, and this is more if fastness of molecules means usually you have hot, and slower molecules as ensemble means that the gas is cold. That's why cold dark. And then basically we have these blue points, these thousands of experimental points, and we have maybe 10. I think it's only 10 free parameters. It's almost nothing for so many experimental points, and you get them fixed relatively well. So you fit in the curve, you get the parameters, you get all the stuff out that you think your model needs to contain. By the way, what you see down here, this is basically the residuum. This is the measured curve, measured points minus the fitted curve, and this is of course where you want to have an equal scatter of plus minus. So here I would almost say there might be something else sitting on top. Or they have forgotten something in the foreground, subtraction. That is nearby because it has a certain dimension. So from this comparison of theory, of fitting theory to our experimental value, we get no stuff out. This is basically, suddenly this freckle size mattered a lot. And what do we get out? One of the parameters is obviously the Hubble parameter, which is then 67.8 plus minus 9 kilometers per second megapascal. And here it's now interesting because these other guys from the standard candle, the supernova type 1A, they have 70 plus minus 1. It means the arrows exclude themselves. Discrepancies. Is this model incomplete? And every model is incomplete. It's just a question to which degree is it incomplete. So, but basically we get now the expansion speed of the universe since this time when this decoupling of matter and radiation happened, when atoms formed. Now, well, back then, it's quite interesting that we had 63% of the universe was filled with dark, of the energy density in the universe was filled with dark matter. 12% was atoms, 15% were photons, so light particles. So obviously this is just when it happened, already a process. And 10% were these mystical little shitters called neutrinos. We come back then when we talk about the inner workings of our sun. Nowadays, it seems 5% visible matter, 5 times as much is dark matter, and the rest of the energy density is nowadays, well, bit is still there in photons, but this cannot be negligible. Because the photons have lost so much energy because the expansion of space underneath them. Redshift due to the growth of the universe. And then there is this dark energy. So basically 5% of the universe we think we understand more or less. So the theory of light, quantum electrodynamics, that is the best understood theory. But the other 95%, we see effects that we would associate with them. Dark matter, I'm pretty sure, but what it is, we have no clues. No clues. There were for dark matter, then for different things where I wanted to come back later. One is weak interacting massive particles on the elementary particle scale, but the experiments should be now sensitive to them. That we haven't seen them yet. There were one claim, but it was then quickly ruled out. Yeah, so for the physicist amongst you, perfect situation. This is brilliant. This is like before quantum mechanics. We know that it must be much richer. It must be much more interesting than we think it is, and we have no clue. So maybe one of you basically stumbles over it and becomes the new Max Planck. Complete revolutionary. Well, so dark matter, dark energy, no clue what they are. And remember this energy density in total. This is basically radiation, the matter, radiation, then here would be the matter. And here radiation almost gone. This is the matter. That's the curvature and this cosmological constant. And now this is maybe where we think this could be we need to include this in order to describe the dark energy in the cosmology. But parts of it goes also certainly to the curvature of space. But what is now this curvature of space? What is this critical energy density? Do you remember? This, how will the universe evolve depending on the critical energy density? Do we have more than we need to get the big crunch? Do we have just enough that the inflation stops? Or do we have not enough and the universe will expand further? So from this data we can extract that we just have enough to come to a hold, but then comes the experimental error. But at the moment it doesn't look good for the big crunch. It looks like this again expanding. What means the universe will grow density of all the stuff in the universe will drop and drop and drop and drop and drop. And at some point, the last star has burned out his last fuel, and there is no light produced anymore, and it will be cold, dark. But the good thing is, this is first of all so far away that we don't need to worry at the moment, and this is our current picture and understanding, which we know is incomplete. So there will be certainly more to come, and hopefully some of you will contribute. That must be my job. Okay, but now it's the question, what is the universe? What is the geography? Is it okay what the teacher told you? So basically, if this here is 1, remember, the sum of the angles in the triangle is 180 degrees, or if it deviations, forget about it. Can't really measure this. So at the moment, we can say the universe is flat. At least the universe, if the Earth is already needs to be a sphere, the universe is flat. And in terms of cosmology, well, it doesn't look too good. So we have just this 1. We would get, well, at the moment it looks anyway, this dark energy faster and faster expansion. But flat would of course mean originally that it stops without dark energy. So these are the models. Relative size of the universe, when we say now, is 1. Then we go back in time, and then with dark matter, dark energy contribution, and what will happen. And if you would have 5 times more matter, then we would have, well, go back here, and at some point a big crunch. And we would see that the universe is a certain age old, about 7 to 8 billion years. We know that the Earth is already 4.5 billion, and the Sun is roughly 5 billion years. And the material which is in our solar system present is very likely being made in a nova that cannot be happened before 7 billion years. This is already what we could say just from our solar system, that we say 7 billion years is the minimum age. Yeah, very likely our Sun is, the nova that exploded there was made of material from another nova. So we are basically 2nd or maybe even 3rd generation star. That means every atom in your body is participated, but very likely at minimum 2 supernova. Star explosions. Okay. And now we can basically use these findings that we have and fix what is not only the future, so the red stuff, the universe will grow and grow and grow and grow at the moment. But we can also go back, and then we get the age of the universe. And at the moment, this is what I think from this Planck data from 2015 is amazing. That they, not that they get 13.8 billion years. That's the age of since big, or plus this 400,000 years of the. Now this is the stuff. So 3 times as long as our 2 to 3 times as long as our Earth lives and Sun lives. But I think what I almost can't believe is this error margin of plus minus 20 million years. This is almost so good. Obviously, they neglect also systematic effects. And just from the precision of their data, because of this enormous resolution. Okay, so at the moment it doesn't look good. The universe would end cold and dark. Doesn't look too nice. But it's not the end of the world. And even this stuff is not understood. completely. So some here, this is even too big and cold of a spot. So open questions are still in this plug data. This hotspot is a bit too big. Then if we go to north and south in terms of our equator, we would expect that temperature effects ease out. In average, the north is as hot as the cold. But it doesn't really look like, but the north is on average a bit hotter than the south. For once it's different. So felt it's always southern hemisphere, they have the sunshine, they have the good weather. We here at the north, we sit then with the rain and blah. So there are a couple of anomalies that are still there, but we can't explain. It should not be at the beginning. There must be something that we don't have in our models yet. Obviously, there is something at latest dark energy. But dark energy doesn't seem to have played a role at the very beginning. Then there's something what they did also is the polarization of these waves, light waves. What is polarization? Well, if we look at wave, it's remember this electromagnetic radiation. That means we have this electric field, and if we would put in a charge, it would swing nicely along depending what the wave is doing. Some of this electric charge might even get accelerated. That's what we use nowadays in particle acceleration. So they do basically like a surfer, like surf on the wave. But it would go here along depending if this is the electric field, and then we can have the swing in one plane. Then we talk about linear polarization. But we can now also sit on the tip of this electric field vector. So if we are here, it's basically swinging always in the same plane. And this can now also go in a basically like a screw-like motion, because the light wave is moving forward with a certain momentum, which is given by Planck's constant divided by the wavelength. So it gives us a direction motion, and then this electric field vector is always perpendicular, and it can change the orientation and go basically in this right-handed curve. No, yeah, that's right-handed. Well, it can also be elliptical, but usually it would be then, so if we project it down here, we can have right-handed and we can have left-handed light. This is left circular polarized. And every other movement we can build up out of these two as a superposition mathematically, that vector 1 weighted with a factor plus vector 2 weighted with the second factor. We would get, for example, elliptical polarization. So we can have this linear and circular, we can build up every polarization. And now there is one effect that is called basically, this should be Thompson scattering, that the electron comes in, where the light comes in is not polarized, and then hits an electron. This electron is now accelerated depending on, and this electric field. And there comes another property in that makes it all complicated, how the electron is rotating. This defines as another plane. The electron is moving in there, and when it's moved, it absorbs the wave and then it re-emits, but in the plane it's moving. And if it's emitted in this plane, means the electric field vector is now swinging there. And we have made unpolarized to polarized. So the outgoing wave is now polarized. This Thompson scattering of the free electron again, we get basically unpolarized to polarized. What means the requirement is the photon must be able to propagate freely. So at the end of this period of recombination, but there were still some electrons around. They would polarize it. And a thin plasma, like at the very end, we learn basically then again still about this period by looking at this polarization. And this is, but then here is the problem. Since this light has been produced, it might have been scattered on electrons that are simply in the around. That might make us this fake pattern. So there was in 2014 a claim in this polarization pattern of the microwave background that there might be also hidden gravitation, the signature of gravitational waves in this expanding part of the universe. So this very strong expanding part might have created gravitational waves, which then might have put on some stamp on this pattern of polarization of the electron distribution. There was a claim by 2014 by the BICEPS collaboration, which is background imaging of cosmic exogalactic polarization, which is located at the South Pole. Planck had a look into its data and said, bollocks, what you see is the foreground. So we got to be very careful, which is basically the reionization phase. Happened in the reionization phase, what means when the electrons and nuclei basically divided. Oops, sorry. Oops, what happens now? They're divided again. So there was nothing here. So this was this claim. Many people were quite upset. So stop share. Why? Because then, of course, if you have such a claim for the first 2015 before LIGO, what means this would have been the first direct observation of gravitational waves. There is a Nobel Prize in. Then immediately the universities were quick. Everybody wants to have Nobel Prize win, possible Nobel Prize winners, and people were then young people were given positions. Then it was rejected. And there's a hard competition of academic positions, and people now given on just, and the way they did it, they made a press conference. The usual way to disseminate scientific results is usually you get your ass down, you write a publication. This publication is then peer reviewed by your colleagues or by some colleagues, which look also at the data analysis and whether it's reasonable what you did. And this was here missing. So there was a lot of bad blood afterwards. Yet I hope you enjoyed this lecture about the baby photograph of the universe and seen why basically this resolution matters in this case. And feel now about a bit more confident about what is where does this dark matter comes from at the moment, is what we talk later about, but also this dark energy. Okay, next week we basically go then past the dark ages, that means after the baby photograph when everything was atoms, until we had gravitational things again created. They were big enough to accumulate gas, and when you press gas together, well, when you pump up your tire in the bicycle, what happens? The pump gets hot. You compress gas, it gets hot. That it became so hot that we had a reionization. Create plasma again, then this plasma might burn in another way and create light again. So when the stars are born. Next week we talk about start the life cycle of stars, which will take 2-3 weeks. And they are mostly about next week about stars are born, and stars how they live, and then in the end how they die and what causes they live. Okay, I think I stole enough of your time. See you Monday for the call.